Now we'll have the presentation from Anton, Khvalyuk from Grenoble on localized collective expressions in disordered superconductors.
Okay, hello everybody. Thank you for still being here, and thank you the organizers for this wonderful opportunity to talk about strongly disordered superconductors and 2D systems, as well as the exceptionally warm reception. I'm really grateful for that. And
What a word!
Well, warm. That particularly important choice of words. So today I'm glad to present you a work on the theory of strongly disordered superconductivity, which was carried out in a wonderful team of theoretician Michael Feigelman, experimentalist Thibaut Charpentier, Nicolas Roche, and Remarque, who is here. And so my talk will consist of 4 parts. Firstly, I'll briefly describe why we're doing this and what's the main theoretical framework I want you to think about. Then I'll discuss briefly flesh out the Hamiltonian and the model that we use to address those experimental challenges. Then I'll show you the results that come out of this approach, and in the end, we'll discuss some important consequences of our research as well as possible further development. So let me start by thinking about what we call actually a superconductor. As it was discussed just before me, we as phenomenological people would just say something that superconducts, has Meissner effect, and I would also add to this list Planck quantization. And if you try to encode this mathematically, you will arrive to London equations, no questions about it. This is literally what you get when you impose those properties. And importantly, this equation defines for us the material property, which is London penetration depth. It is the quantity that material wants you to communicate when it says it's a superconductor. And this should be contrasted with the theory. Of course, there's a wonderful conventional classical theory which is based on the seminal ideas of Bardeen, Cooper, and Schrieffer, which promises us, despite having advanced considerably since the early days of the theory, it still more or less promises us the same things: spectral gap, exponential temperature dependencies of most physical quantities, various statements about disorder dependencies. But what I would like to highlight is that it's a theory that just tells you one way from which a superconductivity can arise, whereas this equation is pretty much a statement that your material is superconducting, and you should not confuse the two when you are doing experiments. Let me illustrate what I mean by first examining what the theory promises us if we follow its assumptions and limitations. So, firstly, the main premise of the theory is that material has to be a good metal in the normal state. And there's one good signature of that. If you examine the resistance curves above the transition, you see that it is weakly dependent on temperature at the scale of Tc itself. So you see this sudden jump, of course, up to BKT stuff going somewhere here. And we say that this is the normal state because the inverse penetration depth is 0, and this is superconducting state because we see a superconducting response. And hand in hand with this prediction goes a statement about the single particle density of states, which is that in normal metal, where inverse lambda is 0, we have a flat density of states. It's a good metal again. Whereas at the scale, at least, of the superconducting scales, whereas in a superconductor, you have a sudden formation of this possibly broadened BCS peak and the sharp gap. And importantly, from the existence of this sharp gap in the single particle density of states, we derive that all physical quantities depend exponential on temperature, and the penetration depth itself is one good example. However, we should not forget that this all again hinges on the premise that our electrons are in a good metal situation, although behave classically most of the time. Specifically, the de Broglie wavelength is much smaller than any other typical length scale, such as the mean free path or coherent length. And then we should ask, well, at least one might rightfully ask, what happens at really strong disorder when this assumption breaks down? And there's practical interest in that because, I mean, naturally we expect this resistance to grow, and naively penetration depth should also grow, but we obviously understand that this cannot happen infinitely long. And yet the question is, so what will be the physics close to this transition to an insulator? And to answer this question, meet films of amorphous indium oxide. Those are films where you control the disorder at the production state. And importantly, the resulting disorder is atomically homogeneous, meaning that to actually see that it's disordered, you have to go down to atomic scales. There is no notion of grains there, at least in normal state, and all characteristic energy scales are in like electron volts, atomically large. So let's see how this material behaves compared to what we expect conventionally. Well, at weakly disordered films, we see that they are properly metallic at higher temperatures, and that demonstrate a relatively sharp transition, so almost a textbook picture. However, at strong disorder, we see that there's no signs of a good metal situation here. The resistance, if anything, it actually grows before turning superconducting, and some samples never, in fact, become superconductors. You see, they demonstrate that this reentrant behavior. However, undeterred by this, we can examine the single particle density of states. Here you can see the evolution of this density of states as a function of temperature, as a function of bias voltage for various temperatures. And here this dashed line corresponds to transition temperature determined from the distance. And the first striking observation is, of course, that there's a high gap in this density of states, even above the transition temperature, which means that, which is explained by the fact that Cooper pairs actually form above TC, and the gap itself is no longer an order parameter. And moreover, the sheer value of this gap is pretty large, so it immediately violates any BCS-related predictions as to the value of this gap. And another consequence of that, for us theoreticians at least, is that we can throw away the life of quasiparticles at low temperatures. They cannot explain any physics that's going on. The Boltzmann weight will just kill them instantly. However, what is a kind of proxy to the order parameter here is the coherence peak height. You see that those peaks appear only below the transition, and the height grows as we go further away from this transition. So it makes sense to try to exploit this analogy further and repeat the experiment at different points of the sample to study actually the inhomogeneity of the resulting superconducting state. And before I show you the actual result for the histogram, the distribution of those height, let's discuss what we expect naively. And it wouldn't be a surprise to know that actually we expect something like a narrow, boring Gaussian distribution around some value that characterizes the mean order parameter, maybe with some tiny fluctuations. And this is not at all what happens. Instead, you see that it's not even symmetric, let alone Gaussian. It's a rather broad distribution, heavily skewed, and this just goes to say that the material is in fact strongly homogeneous, the superconducting state in particular, and this basically destroys for us the classical theory. So the only thing we are left with is measuring the only physical quantity that actually knows something about the superconducting state. So here you can see the behavior of the relative change in this penetration depth of the function of temperature measured by microwave resonators. And the striking feature is that instead of those exponential dependencies, we see something that resembles a power law with relatively low power, relatively low exponent, and the sheer magnitude of the effect you see up to 1% for most disordered samples, which are on top here. All of this just goes to say that there's no conventionally accepted explanation for this kind of behavior, be it Cooper pair breaking, various collective modes, maybe surface contaminants like two-level systems. All of this can be ruled out either by these curves themselves or by disorder dependence of those curves. And the story repeats itself for the dissipation. Here you can see that most of the internal quality factor of those resonators, which is just for our purposes the inverse dissipative conductance. And again, we expect this quantity to grow with a decrease in temperature, or at least to saturate, as it was in Peter de Visser data that we saw earlier in this conference. But instead, it actually decreases as we increase temperature. And again, this begs for explanation, and with all the trivial ones quickly ruled out. So I will spend the remaining some time. Oh yeah, sorry. Yeah, that's good. Let's just share probably. Sorry for that. So yes. So I'll spend the remaining 15 minutes to convince you that all of this behavior actually is intrinsically tied to the inhomogeneity of superconducting state. And to this end, let me quickly present you the model the theoretical model that we use to explain all of this. And to start, I have to present you the understanding of these weird resistance curves that explains the outline. Essentially, the statement is that this normal state is a different kind of state. It's not a boring insulator; it's an Anderson insulator with a large localization length, which means that electrons are now localized somehow in the region of the typical size of psi. And on top of that, those electrons bind into Cooper pairs, but due to certain attraction, let's say phonon, like typical attraction in the Cooper channel, like phonon mediated one, but they only do so locally, which explains to you the appearance of this gap in the single particle density of states. And it is only at lower temperatures and not for very strong disorders when this attraction wins over globally and the sample becomes superconducting. So how do we encode this physics? The first step is to actually reflect the absence of unpaired electrons by, well, just knowing the corresponding states from our Hilbert space. So the first step is really to say that our Hamiltonian will act only within the subspace which contains no unpaired electrons. We then straightforwardly encode the non-interacting part of the system by just writing particle Hamiltonian in its eigenbasis. And here, psi's are some energies of the single particle states, those localized states, and for our purposes, we just assume that they're random, and of course, the particular distribution is not important for physics, be it box one or something that you like more. And then we add the interaction term, which just says, well, electrons rather still attract to each other. And in practice, it just means that they can hop from one localized state to the other as a Cooper pair, because remember, there's still no unpaired electrons. And of course, it is important what is the structure of the matrix elements of this model. And of course, they are governed by the underlying physics. Here, I express this matrix element in terms of the overlap of the squares of the individual single particle state squares, because those are, in fact, Cooper pairs. And this residual energy dependence just tells us that there's some underlying mechanism, let's say phonon-induced attraction. And at this point, we assume that disorder, while being strong enough to challenge superconductivity, leaves phonons intact, so they can still mediate attraction as before. And you see, this object is not at all something innocent, because these individual wave functions are themselves not just exponentials that smoothly decay at distance xi. They are in fact very rough objects. They fluctuate strongly within their localization volume, and because of that, you wouldn't be surprised to know that these properties directly translate to the matrix elements. So they also, while decaying on average with distance between this, let's say, centers of those localized states, they fluctuate strongly within this typical distance. For instance, here I'm showing you a numerical evaluation of this overlap for a reasonable model of those single particle wave functions, and you can easily see that they can differ by an order of magnitude. And now I'm making this dirty theoretical trick by saying that we'll model this by a binary distribution, which is that we just say, first of all, if the states are too far apart, they don't interact. And secondly, even if they are close enough, they might as well accidentally have small matrix elements, and let's just throw them away in this case. And the model then is that each single particle state talks randomly to some subset of the available local neighbors. And to further simplify our life, we say that the corresponding matrix element is just a constant, which defines for you what is the dimensionless Cooper coupling constant in this model. And moreover, we say that the number of neighbors is in fact constant. And it looks quite weird. I agree with you. This was my reaction just as well. And that's why I spent some time studying a more physical model where you relax this weird binary distribution to some more physical one. And it turns out that nothing really changes. You just reassign certain letters and then arrive to the same model again, at least in terms of results. That's why we'll work with this one, because it contains explicitly a nice property, which actually connects to the previous discussion, that we can microscopically observe the notion of a graph of interactions, which is somehow embedded in real space. And moreover, this graph actually has certain locally tree-like structure. Let me explain now what I mean by this latter statement. So let's perform the construction of this matrix element as I've just outlined. Like those little dots here are centers of individual localized states. Let me select just one, this green one here. And this circle now is its localization volume. Within this volume, we randomly select k neighbors, here 5, k plus 1. And I've highlighted them with larger size. And then we say that because they now interact strongly, I draw this line, which is the matrix element. And we're about to carry out this process further. That's why, in addition to tracking the real space structure, which will quickly become rather messy, I would also like to track the topology of this network, meaning just the structure of who interacts to who. And if we now repeat this process for all the neighbors that we've just selected, in real space, it's just diffusion. Of course, it's going to be messy. But in this topological sense, this is a nice structure, a tree-like structure. And we theoreticians, in fact, really love this structure because it allows a lot of theoretical methods like belief propagation and other nice analytical techniques. But importantly, this only holds up to a point. If you continue this procedure further, you'll observe that eventually this nice structure is violated, and violently so, loops proliferate throughout the system because it just learns that it is actually a 3D sample. It cannot have a tree-like structure indefinitely. And importantly for us, there's nice division of scales that at small scales, this is indeed a tree-like structure, and that's why we say that it's a locally tree-like structure. However, at large scales, it properly encodes that this is not an abstract theoretical model, it's a real model of a 3D material. So we are able to ask about microscopic conductance and all that. And essentially, this is another step that we have to make. Even if we are able to do something about small scales, use all the analytical tricks we like, this still doesn't give us the way to the large scale response. And the answer is to use the network model, which will look surprisingly familiar, except that with the only difference that I'm about more or less to derive it. The idea is that let's consider a sample of this geometry, the experimental one, and apply a microscopic phase gradient to this sample. And we know that because of London equations, there will be some total supercurrent. However, microscopically, what has to happen is that each single particle state has to has to conserve charge, and that's why all the current that flow in the system has to obey this trivial condition restricting currents from one state to the other. Moreover, because we know that if we switch off interaction, the system is insulating by construction, all charge transfer happens only via interaction, so that we know that current can flow only at all those edges. So you can already see how this network model emerges. And finally, to make this system a meaningful one, we also have to say what is the linear response of this system to phase gradients. And the idea is that out of purely gauge invariant reasoning, you can argue that local currents have to respond in a linear fashion to small local phase gradient. However, here it's important that each individual response is a random, strongly disordered quantity that is determined from microscopics by this small scale theory, and phases here have to be adjusted to conserve charge. And it's important that it's not like I've derived it to you in a true sense, and it's not like this conventional Jollison junction array model that you typically see in the literature. To derive this equation, you first have to restrict yourself literally to zero frequency, the superconducting response, and even then deriving this takes quite an amount of time and relies heavily on this locally tree-like structure. But this is a discussion for some another time. In modeling, once you have this network model, as the previous speaker already spoiled it, it's not exactly that you just say, oh, okay, the macroscopic conductance is this, like some semi-classical expression. Instead, you have to honestly solve this resulting network model, and we know that the result will heavily depend on the structure of your network and the distribution of the conductances. For instance, here I'm showing you the trivial answer for just a chain. We all know how it's going to look like. However, if you go, let's say, to higher dimensions, all becomes suddenly much more complicated. In general, there's no closed answer, closed form expression for the conductivity of the system. You have to impose additional assumptions on the distribution function of those individual local conductances. Finally, it has been already mentioned that you can get away with certain large Z approximations when you live in higher dimensions. But again, this is a large Z expansion and it's not always valid. And you wouldn't be surprised to learn that in our case, the conductivity is a complex interplay between the structure and the distribution of individual responses. And for our system, in fact, it becomes interesting just in and of its own to compute the macroscopic response. And you might try to guess which one of these actually applies to our system. And the correct answer to this question would be that I forgot to specify the distribution, right? So at weak disorder, this weak disorder expression does work, and that's why you reduce to your standard semi-classical expression. So everything is consistent here. However, at strong disorder, it's really a hard problem. So we resort to a number of tools, numerical analysis. We use certain analytical techniques to tackle it, and it's an interesting subject, but a story for another time. So let me just quickly show you the results that come out. So firstly, here's the resulting temperature dependence of the macroscopic response in the same way as the experimentalists plotted as a function of temperature, and we can easily see that it also resembles a power law, and the value of this exponent is more or less similar to the experimental one, at least for the most disordered simulations. And the nice part about the theory is that we can actually spell out the result analytically. So here it's explicit form, and most importantly, it contains the distribution of the order parameter in the system, and specifically its low value tail, which is selected by this integrand. And in fact, the story repeats itself for the dissipative response. Here I'm writing it down as the inverse quality factor of the resonator, but this time the relative scale of the typical order parameter is not temperature as within this case, but frequency. And let me also quickly show how the second expression behaves. So here we can see the plot of the quality factor as a function of temperature, and just as with the experimental data, it grows with temperature initially. And in fact, this particular observation alone invites a certain interpretation that our system has some kind of localized two-level system-like excitations that initially provide this cotangent-like behavior, but because as temperature grows, the spectral density increases, and that's why this curve departs from the cotangent part. And just by looking at the expression that we obtain, we can speculate about the local structure of those excitations. However, again, at this point, further study is needed to actually claim anything. Importantly, we also can study the spectral density of those excitations. Here you can see it as a function of dissipative part as a function of frequency. And importantly, this is a very steep curve. And whereas currently experimental tests, they are situated somewhere here, and I say here plausible because it's not really a quantitative comparison for now. And the nice part again about the theoretical results is that we can actually invert this equation, express the distribution of the order parameter, which yields for us a probe for this distribution function. At least its low value tail. You just take your quality factor, the function frequency, and hopefully get something out of it. And yeah, let me just quickly go to conclusions. The first important thing that comes out of this discussion is the particular shape of the superconductor insulator phase diagram. And usually we're used to seeing something like that. However, if we zoom closer to this region, which was done experimentally by Thibault and Benjamin, we see in fact that as we approach this transition as a function of disorder at low temperature, we see a jump in the superfluid stiffness. And to understand the jump, we have to argue that it is actually a first order quantum breakdown, quantum phase transition of the superconducting state. So there has to be another phase which has its own non-trivial order parameter, and in this case, it turns out to be Cooper-Perry glass. Why is that? Again, is a separate discussion. But once you accept that, this jump looks kind of inevitable because those are incompatible orders, so they have to result in a first order phase transition, which in our case is naturally described by equality of free energies. And now, because we know that in the Cooper-Perry glass part, the free energy behaves as a function of temperature as a force power of temperature, which is an actual consequence of the standard weak Coulomb gap. And in the superconducting part, instead of the standard exponential dependence, we have also a power law granted to us by this localized bulk excitations. It means that the shape of this first order transition line, in fact, has a weird unconventional direction. Instead of going like this, it actually bends rightward as we increase disorder. And this, in fact, is a nice explanation for the reentrant resistance curves that we see in those materials. So if the disorder is supercritical, so this blue line, as you lower down the temperature, you first pass through the superconducting fluctuation region, and that's why your resistance drops initially. But then you discover that you're suddenly in Cooper-Perry glass phase, and that's why your resistance shoots up. And importantly, this is a direct consequence of this unusual direction of the transition line. However, all of this is just a solid but qualitative argument, and the proper theory is non-existent. It's a work in progress. And in conclusion, the key ingredient to all of the theory is the underlying homogeneity of the superconducting states, which results in our case to those bulk collective, allegedly two-level system-like excitations, which in turn more or less define the low energy physics. And of course, this story is far from over. For instance, this theory ignores quite a number of things. And secondly, there are materials which, while not particularly suitable for our theory because they contain grains from the outset, I'm talking to granular aluminum here, they demonstrate remarkably similar phenomenology. For instance, recently people tried explicitly measuring low energy excitations and observed the presence of huge dipole moments, I mean, by no means can you explain this as some sort of atomic scale, which goes some way towards speculating about the similarity between those systems. And yes, with this, I'd like to thank you for your attention, and I'm ready to take questions.
We have time for one question.
I'm interested in how you mentioned it, but maybe I lost it. So if you can clarify how you construct the network from, you said that you have your Hamiltonian and you put constraints on basically the Hamiltonians, and then how, when you solve the network, do you solve it also numerically with open boundary conditions, finite ties? I don't know.
So the first part is that the exact shape of the network comes from microscopic model. So it's not like we just draw it by hand. In practice, what I do is that from numerical simulations, I just literally simulate a huge instance of this interaction graph, like 1 million sites. Then I construct the matrix element according to this procedure. Then I sample the individual responses from solving the Hamiltonian for this instance of the graph. And by solving, I mean using the belief propagation, because you cannot diagonalize 10 to the 6 degrees of freedom. And then I solve the macroscopic response problem in the similar way that you did, while also controlling for finite size effects just by scaling my system or cutting pieces from it. Control for the distribution of the resulting responses, and for this I can actually show you one extra slide. So it's the let me quickly find it. This one. So, for instance, here this result, the numerical result for the dissipative conductance as a function of frequency obtained by direct diagonalization of this system. And the problem here is that let me show you another picture as well. So, for instance, here is the plot of the resulting macroscopic responses as a function compared to what you would expect from percolation theory. And while you see that in general it aligns pretty well, and I am quite able to explain all the deviations, individual sample-to-sample fluctuations for strongest disorders may be up to 100%, so you have to carefully control for those.
When you say percolation theory, you mean in effective medium?
No, effective medium is large, it's weak disorder